Hi everybody, I am MANOJ Deshmukh. Today we talk about the one important article in the linear algebra, that is linear transformation. Linear transformation. The first question is arise that what is linear transformation? We call it as a linear transformation. Basically, it's a very simple answer. A linear transformation is a function, and this function satisfies two conditions. This is a very simple definition. What is a linear transformation? A linear transformation is a function, and this function satisfies two conditions. Now the problem is that which function is a linear transformation and what are the two conditions? First, everybody must know that function means it has a domain and it has codomain set. It has a domain set and it has a codomain set. So here in a linear transformation, we take the function and the domain is one of the vector space, and codomain is also a vector space. So it is clear that a linear transformation is a function from one vector space to another vector space, and such a function is denoted by the notation T is a function from one vector space to another vector space. Okay, that vector space we denote by the V notation, and the codomain set is also vector space. It is denoted by W. So a linear transformation T is a function from one vector space V to W. The next question is, if it is a function, then this function must satisfy the two conditions. Okay, what are the two conditions? The first condition is that take any two vectors in domain set. Okay, that is for all u bar and v bar. These are the two vectors, any two vector in the V set, and such that the condition is T of u bar plus v bar is equal to T of u bar plus T of v bar. This is the first condition. Second condition is that take any vector for all u bar belongs to V, that is a domain set. One of the scalar k belongs to F. So here we take the field is a real number R, such that T of k times u bar is equal to k times T of u bar. So this condition should be true for any vector u bar. Mean a function T from one vector space to the another vector space W satisfy these two conditions, T of u bar plus v bar equal to separate images T of u bar plus T of v bar, and second condition is that T of k times u bar equal to k times T of u bar. If any function satisfies the two, then such a function T from one vector space V to W is known as linear transformation. transformation. If one of the condition is not satisfied, then such a function is not a linear transformation. Okay, let us consider the example. Okay, suppose T is a function from one vector space. So domain is a vector space. So we consider the simple vector space R2 to R2. So domain is a vector space and codomain is also vector space, two-dimensional, two-dimensional. Define the function T of u bar is equal to. So T of u bar is a vector in R raised to 2. So u bar has a two components, say x comma y equal to. So xy is a vector in R2. So its image T of xy is also a vector in R raised to 2. So it has two components. So let us consider the first component is x plus 2y. And here we consider x plus 1. Consider this function in this way. And here we have to check. You have to check T is a linear transformation. Okay. So it is clear that T is a function from one vector space to the another vector space defined by this function. We have to just check that such a function is a linear transformation or not. So we have to check the conditions. We want to check the conditions. Check conditions of linear transformation. The first condition is that take any two vector u bar and v bar in the domain set. That is, domain set is R raised to 2. R raised to 2 such that T of u bar plus v bar must be equal to separate images T of u bar plus T of v bar. Okay. So let us consider the two vector in R raised to 2. How to check this condition? So take the two vector in R raised to 2. Let u bar and v bar are the two vector in R raised to 2. So u bar and v bar have a two components. So u bar equal to u1 u2 and v bar equal to v1 v2. These are the two vectors in the domain set, that is R raised to 2. Okay. We need to find u bar plus v bar. So u bar plus v bar equal to. So we take the component wise addition u1 plus v1 comma u2 plus v2. This is also vector in R raised to 2 because R raised to 2 is a vector space. Now find out the image left side T of u bar plus v bar. So T of u bar plus v bar equal to T of u bar plus v bar is already, this vector is here. So u1 plus v1 and u2 plus v2, which is equal to. Now see what is the function is given. T of xy is equal to, image of this vector is, the first component is x plus 2y, the x plus 2 times y. So here image of this vector is x plus 2 times y. And the first u1 plus v1 plus 2 times this, 2 times u2 plus v2. This is the first component. And second component is, if you observe that x plus 1. X plus 1 means the first component of the vector x added with 1. So here also the first component is this u1 plus v1 added with 1. Okay. So this one is here we call as the first equation. Now we calculate this side T of, now we can calculate the right side of that, T of u bar plus T of v bar equal to T of u bar means u1 u2 comma u2 plus T of v bar means v1 v2. Now we find out the images of this. And the function is given t of xy is x plus 2y. So this is x means u1 plus 2y. 2 times y means u2. Comma. Second component x plus 1. The vector whose first component x plus added with 1. So here first component is u1 plus 1. Plus. Similarly, we can calculate the image of this vector v1, v2 under t. The formula is given that x plus 2y. X means v1 plus 2 times v2. And the second component is here x plus 1. X component added with 1. X component v1 added with 1. Now we add these two vectors here. Component y. This component is added to this component. This component is added to this. So u1 plus 2 times u2 plus v1 plus 2 times v2. Second, u1 plus 1 plus v1 plus 1. Now if we simplify, what happened? u1 plus v1 plus, you can take the 2 is common, u2 plus v2. u1 plus v1 plus 1 plus 1 is 2. We call as a 2. Now we observe here. So this is t of u bar plus v bar. And its image is this vector. Okay. And t of u bar plus t of v bar, we calculate this image is this vector. If you observe these two vector, equation 1 and 2, the first components are same. u1 plus v1, 2 times this. u1 plus v1, 2 times this. But the second component here, u1 plus v1 plus 1. And here u1 plus v1 plus 2. So this is 1 and this is 2. The second component of these are not equal. So these two vectors are not equal. So right hand side of 1 and 2 are not equal. Not equal. Therefore, their left side, these two equations, their left side means t of u bar plus v bar and tu plus tv. Therefore, t of u bar plus v bar is not equal to t of u bar plus t of v bar. Therefore, the given function t from vector space R2 to R2 defined in this way, okay, is not a linear transformation. So this is very good example that this function is not a linear transformation. Now let us consider the another example. Let t is a function from one vector space R2 to the another vector space R2 defined as, this function defined as t of, so take any vector in R2, its components xy is equal to, its image is the vector in R2, it has the two components, so we consider x minus y and here we consider y. The problem is that is such a function, is t a linear transformation? Linear transformation? Question mark. So again we have to check the conditions here, two conditions. What you have to check? First condition is take any two vector u bar and v bar is in the domain r raised to 2 such that t of u bar plus v bar is equal to separate images t of u bar plus t times v bar. And the second condition is that take any vector u bar in the domain set R raised to 2. Take any scalar k belongs to field A, and suppose the field is a real number such that T of ku bar is k times T of u bar. So we have to check the two conditions here. So we check the first condition. For that we need the two vector in R raised to 2. For first condition, let any two vector u bar and v bar in R raised to 2. As u bar is the vector, I consider here x1, y1. Suppose the vector v bar is x2, y2. These are the two vector in R raised to 2, that is the domain set. We find out their addition, u bar plus v bar, because that addition is we required here, x1 plus x2 component wise, and comma y1 plus y2. Now we find out the left side of this condition. Left side of the condition first, that is T of u bar plus v bar. T of u bar plus v bar is already we evaluated here. So we consider this value vector. Okay. Now we evaluate the image of this vector. The formula is here that T of xy is first component is x minus y, which is subtraction of these two component, comma second component as it is. The same here, the subtraction of this x1 plus x2 subtraction minus y1 minus y2, comma, and second component is as it is, and we call that the first here T of u bar plus v bar. Now we evaluate the right side of that, right side of this side, T of u bar plus T of u bar. T of u bar plus T of v bar equal to T of u bar vector means x1 y1 plus T of v bar vector means x2 y2. We evaluate the image of this vector under T. The formula is here. T of xy means the first component is subtraction x minus y, comma y component as it is. In the same way, T of this vector is x1 minus y1, and second component is y1 as it is, plus T of this vector, that is the image of this vector under T. The formula is defined above that, subtraction of the two, x2 minus y2, and second component y2. We add the two vectors. So addition is component wise, add the first component and add this. So x1 minus y1 plus x2 minus y2, y1 plus y2. So we simplify x1 plus x2 here, minus y1 minus y2, y1 plus y2. So we call as a 2. And if you observe the 1 and 2, the right side, this vector has a 2 component and this vector has also 2 component. Both vector whose first component is x1 plus x2 minus y1 minus y2, here x1 plus x2 minus y1 minus y2. The second component is also same. Therefore, these two vectors are same. And if the two vectors are same, then their left side, T of u bar plus v bar and T of u bar plus T of v bar, they are same. Therefore, from 1 and 2 we write, from 1 and 2 we write T of u bar plus v bar is equal to separate images T of u bar plus T of v bar. So in this way, the first condition is satisfied here. Now we check the second condition. Second condition is T of k u bar is k times T of u bar. So for second condition, okay, so we need a one vector u bar is R2. Let u bar is the vector, it has a component say x1 y1 belongs to R2, that is a domain set. It is a domain set. We need a one scalar say k belongs to f, and field is real number. Let us consider k times u bar. We need this. K u bar is k times u bar means k. U bar vector means x1 comma y1. And the scalar multiplication of the vector. So as usual, that k is multiplied to the every component of that vector, that is kx1, ky1. Okay. Now we consider the left side of this, t times ku bar. Left side, t times ku bar equal to t of ku bar means we already evaluated, this is a vector, so you can write here kx1, ky1 equal to. What is the image of this vector under t? The formula is given here. T of xy is equal to x minus y, which is subtraction of the 2 comma y component as it is. In this example, the function is defined in this way. Okay. So we consider here subtraction of this kx1 minus ky1, and second component is ky1. This vector is the image of this vector under t. So this is the vector in domain and this is vector in codomain set. So if we observe that in the first component there are two terms, and in the two terms k is the same multiplier factor. We can take the k is outside here from the first component. Similarly, if you observe that k is also multiplied to the second component, so we also take the k is outside. So in the first component k is outside, second is k, so take k is outside here. So k time here x1 minus y1 comma y1. So k. So if you observe that this is the image of which vector? If you observe here, x minus y comma y is the vector which is the image of xy under t. So if it is a vector, then we write this vector as a t of xy. As the same way, x1 minus y1 comma y1 is the vector we can write as t of x1 y1. So this vector is the image of x1 y1 under t. So this is k t, and already we call x1 y1 means which vector? U bar. Okay, so here we write this. So t of u bar, so which is equal to right side of that, which is equal to right side, k times t u bar. Hence t of k u bar, after simplification we get k times t u bar. Hence the function is also satisfies the second condition. Therefore given function t from R2 to R2, that is one vector space to the another vector space, defined as t of xy is equal to x minus y, y is a linear transformation. It's a linear transformation. The linear transformation is always defined, it is always depends on how you define the function. So in this example, this function, if we define in this way, then it satisfied all the two conditions, therefore it is a linear transformation. So today here we discuss what is a linear transformation, and we also consider the two examples here. Q1 is a vector space and another is not a vector space. Thank you very much.